refractive index is equal to C upon V. That is the first formula. Do you remember that we have derived the formula here that speed of light in a vacuum is given by 1 upon under root of mu 0 epsilon 0, right? And speed of light in a medium is denoted by 1 upon refractive index, 1 upon mu in a medium multiplied by epsilon in a medium. Can I write down like this? Sure. Because we have proved the first formula, I can write down the second formula on that basis. Now, if I take the ratio here, I will be able to write down C upon V is equal to, you will be having under root of mu m upon mu 0 multiplied by epsilon m upon epsilon 0. Am I right? What is this mu m upon mu 0? Obviously, the right-hand side will be taken as refractive index of a medium with respect to the vacuum. But what is this? This would be written as under root of mu r multiplied by epsilon r. It's a relative permeability multiplied by relative permittivity that is giving us the formula for the refractive index. So mention that. So this is our second formula for today. First we have done it. This is the second formula. Now, can you tell me what is the refractive index of the vacuum? What is the refractive index of the vacuum? Why 1? Because what we are deriving here is refractive index of vacuum with respect to vacuum. Refractive index of vacuum with respect to vacuum is velocity of light in a vacuum divided by velocity of light in a vacuum. So velocity of light in a vacuum is C upon C, that will be taken as equal to 1. And different medium, will they have a refractive index less than 1? Can it have a refractive index less than 1? Can a medium have a refractive index less than 1? You will always have refractive index greater than 1. So can I say that minimum refractive index is for the vacuum? Maximum? Are you aware? Maximum refractive index? Yes, rightly said. Loudly. Diamond. It is having a refractive index of 2.1. And you can imagine the speed of light becomes half inside the diamond. Diamond is having the refractive index 2.1. So maximum refractive index is for the diamond, minimum is for the vacuum. That is the point that is to be remembered. Second important thing, when you define refractive index of a medium with respect to the vacuum, you are writing the formula C upon velocity in a medium, right? Can I write down this formula as, this will be frequency into wavelength in a vacuum upon frequency into wavelength in a medium. So you will be able to write down refractive index of a medium with respect to the vacuum is equal to lambda 0 upon lambda m. This is my third relation, with lambda 0 is the wavelength, in vacuum, and lambda m is representing the wavelength in medium. right? Correct? Now, can I write down this as refractive index in a medium with respect to the vacuum is equal to, you will be able to write down 1 upon lambda m divided by 1 upon lambda 0. Can I write down like this? Sure. So this is nothing but wave number in medium divided by wave number in vacuum. So we are able to define refractive index in terms of wave number. I can also write down equation 3 in this manner. I'm rewriting it once again. Refractive index of medium with respect to vacuum is equal to lambda in a vacuum upon lambda in a medium. Can I write down this as refractive index of a medium with respect to vacuum minus 1 is equal to lambda 0 minus lambda m upon lambda m? Can I write down? Subtract 1 from both the side, you will be able to get the right hand side in this manner. Can I get it? What will be the relation between lambda 0 and lambda m? What will be the relation between lambda 0 and lambda m? No, that is another part. I am asking you in terms of greater than, less than. What will be the relation between lambda 0 and lambda m? Lambda 0 will be? Obviously, because you have already said that refractive index of a medium with respect to vacuum is greater than 1. So lambda 0 upon lambda m will be greater than 1. So lambda 0 will be greater than lambda m. Am I right or not? So I can find out the change in the wavelength. Delta lambda is representing change in wavelength. Change in wavelength is equal to lambda in a medium in a bracket refractive index of medium with respect to vacuum minus 1. I'm calling this as equation 5. Am I right? I can rewrite this relation as lambda m is equal to lambda 0 upon refractive index of medium with respect to vacuum, inner bracket refractive index of medium with respect to vacuum minus 1. So you will be having this as equal to lambda 0, 1 minus of 1 upon refractive index of medium with respect to vacuum. So wave number in a medium will be more, or wave number in a vacuum will be more? Are you all getting it? Why so? Because our formula tells us that wave number in a medium upon wave number in a vacuum is this refractive index. This is greater than 1. So wave number in a medium will be greater than wave number in a vacuum. So can I have the similar approach here to find out the change in wave number? Just look at it. Can I write down like this? So change in the wave number will be taken as equal to wave number in vacuum multiplied by refractive index of medium with respect to the vacuum minus 1. Can I write down like this? Can I write down? Do you agree or not agree? Disagree? Sure. Similarly, I can write down the another form of this, the change in wave number. Change in wave number, WNO is representing the wave number, will be equal to, you will be having here the ratio as, you are writing wave number in vacuum, so wave number in medium, wave number in medium multiplied by 1 minus 1 upon refractive index of medium with respect to vacuum. Check out whether you are getting the step, because I am skipping the steps at some points. Getting or not getting? You take this term inside. This is 1 will be there, and this term onto this side, 1 upon refractive index. ये relation है सामने. Subtract 1 from both the side. What you will have? Refractive index of the medium with respect to vacuum minus 1. Minus 1 will be here. So if you solve it, wave number in a medium minus wave number in vacuum upon wave number in vacuum. So numerator is change in wave number. That is equal to wave number in vacuum multiplied by refractive index of medium minus of 1. Rearranging the same term, you are getting equation number 8. I can define here refractive index of a glass with respect to water is equal to refractive index of glass with respect to vacuum upon refractive index of water with respect to vacuum. Can I write down like this? The left hand side is read as refractive index of glass with respect to water. This is read as refractive index of glass with respect to water. Right hand side, refractive index of glass with respect to vacuum divided by refractive index of water with respect to vacuum. No, it is in terms of velocity, it is reciprocal. It will come as a reciprocal, but suppose I want to solve this. What I will say, this is equal to speed of light in a vacuum divided by velocity of light in a glass divided by speed of light in a glass, water divided by velocity in a water. So it will turn out to be velocity in water upon velocity in glass. Now that is what you were trying to tell me. So I am able to put down in terms of velocity, it comes in that manner. You can add this one in a different manner. Here I can also work in this manner. This is all refractive index of glass with respect to the water. So you will be having here refractive index of glass with respect to the water minus of 1 is equal to velocity in water minus velocity in glass divided by velocity in glass. So I will be having change in velocity. Change in velocity will be equal to velocity in glass in a bracket refractive index of glass with respect to water minus of 1. Similarly, I will have this as velocity in water in a bracket 1 minus of 1 upon refractive index of glass with respect to the water. Now, before I proceeded, can you think of why I'm doing all this jugglery? Correct? Different forms. Why? So what they are doing, they are also playing with the same formulae and generating different questions for you, which are getting covered by these different formulae. Now, if all these formulae are properly memorized by you and you are able to understand which formula to be applied where, you will be able to get the answer faster. I told you one thing today in the morning, that there are some shortcuts also. Do you remember? Suppose it is given to you that wavelength of light in air is 6000 Armstrong unit, refractive index is refractive index of glass is 1.5. What will be the wavelength in glass? What will be the wavelength in glass? I'll write down the values so that you can solve it. You are having here refractive index of glass with respect to the vacuum 1.5. You are having lambda in air that is given to you 6000 Armstrong unit. What will be lambda in glass? Air and vacuum, we take it as same. You are having all things in front of you. From the board, you can calculate the value. Aa gaya na? It's easy. Nothing is to be done. The first relation that we are having, lambda 0 upon lambda m is equal to refractive index, is to be used. You are having 1.5 on the left hand side. Is lambda 0 upon lambda m. Lambda 0 is given to you 6000, refractive index is given to you 1.5. So you can make a substitution and get the value of lambda of glass, that is 4000 Armstrong unit. Got it? But that is a process. But in an objective, if you look at the option and you are able to see that there is only one option less than 6000 Armstrong unit, there is no need of solving the problem. You can directly mark that and proceed ahead. Am I right or wrong? So you should be aware of that we should also have a look at the objectives, options there, and mark the answer accordingly. Any type of this question could be asked to you where you should be able to report it. So you can find it out, this part. यहां पर हमने निकाल के दिखाया चेंज इन वेलोसिटी के दो फॉर्मेट्स हो गए, चेंज इन वेवलेंथ के हो गए, बाद में फिर आपको मिल गया है चेंज इन वेव नंबर के भी मिल गए. So these are different forms of the equation which we are looking at. These are different forms of equation. Now I can further go on. Will you be able to see on this side or should I rub off? दिख रहा है? Okay. Now I'll require a bigger space. I'll take that side only. Now we are writing here refractive index of glass with respect to the water. We have written a formula, velocity in water upon velocity in glass. Am I right? Now can I write down this as distance covered in water upon distance covered in glass multiplied by time in glass divided by time in water? This is giving you your 13th expression today. Now, if there is a condition that time taken in glass is equal to time taken in water, then refractive index of glass with respect to water will be equal to distance covered in water upon distance covered in glass. Here again I can go for, I will be having refractive index of glass with respect to water minus of 1 is equal to x in water minus of x in glass divided by x in glass. So you will be having the difference in the distance covered in water and the glass, that is equal to x in glass multiplied by refractive index of glass with respect to water minus 1. Or I can write down x in water in a bracket 1 minus 1 upon refractive index of glass with respect to water. Getting different forms. These are all of one type, but you can definitely cover the problem in this manner. So different problems will be framed on the same relation and you can get the answers for that. So that is how you have to look at it. I can further have one more condition here. If instead of time I am having here distance covered in water equal to the distance covered in glass, in that case refractive index of glass with respect to the water will be equal to time in glass upon time in water. Again I find out the change in time, that is equal to time in glass minus time in water is equal to, you are having time in water in a bracket refractive index of glass with respect to water minus 1. This is the one relation, and you will be having this as time in glass in a bracket, you will be having that as 1 minus of 1 upon refractive index of glass with respect to the water. There is one more interesting formula. Suppose you are having refractive index of second medium with respect to first. So we are writing here refractive index of second with respect to refractive index of 1. Am I right? Can I write down this formula as refractive index of second upon refractive index of third multiplied by refractive index of third upon refractive index of 4 multiplied by refractive index of 4 multiplied by refractive index of 1? Can I write down like this? So I will be able to write down refractive index of second with respect to 1 will be equal to refractive index of second with respect to third multiplied by refractive index of third with respect to 4 multiplied by refractive index of 4 with respect to 1. So this is another formula which we can work with. Getting it? पूछो. ये वाला स्टेप या ये वाला? ये वाला. I am multiplying by mu3, dividing it by mu4. Again I am multiplying by mu4, dividing by original mu1. So mu3 is getting cancelled, mu4 is getting cancelled. So you are left out with mu2 by mu1 only. But when we are writing this step, I will be able to call this step as refractive index of second with respect to refractive index of third. This is refractive index of third with respect to refractive index of 4. And that will be refractive index of 4 with respect to refractive index of 1. So you will be having the multiplication chain that could be established here. You can go beyond this. यहाँ पे refractive index of 4 upon refractive index of 5 लिख दीजिए. Then refractive index of 5 upon refractive index of 1. It will continue. Am I right? Getting it clearly? हो गया? Now, can I write down this step? Refractive index of second medium with respect to first medium is refractive index of second with respect to refractive index of first. Can I write down this to be equal to 1 upon refractive index of 1 upon refractive index of 2? Can I write down like this? So, can I write down this to be equal to 1 upon refractive index of 1 with respect to 2? So refractive index of 2 with respect to 1 is reciprocal of refractive index of 1 with respect to refractive index of 2. Done? 18th. Equation number 17. Is it clear with for you? Equation number 17. It is mentioning there if distance covered in water is equal to distance covered in glass. So substitute that value in equation 13. What will happen? If you substitute in 13, distance covered in water equal to distance covered in glass. These two are equal. What would happen? So that is how 17 has been arrived. Okay? Subtract 1 from both the side. You will be able to solve to get 18. Equation number 17, subtract 1 from both the sides. So can you tell me the relation between the refractive index and wavelength? Refractive index and wavelength. They are inversely proportional, right? So can you tell me what will be the relation between refractive indices of different color? I'm not asking you the mathematical relation. I'm asking you greater than, less than. So how are you writing here? Lambda for the violet light is less than lambda for the indigo, less than lambda for the blue, less than lambda for the green, less than lambda for the yellow, less than lambda for the orange, less than lambda for the red. Right? So you will be writing here refractive index for the violet color will be greater than refractive index for the indigo color, will be greater than refractive index for the blue color, greater than refractive index for the green color, greater than refractive index for the, come on tell me, yellow, then greater than refractive index for the orange, greater than refractive index for the red. So red has minimum refractive index and violet is having maximum refractive index. Getting that smart? So can you tell me that if I am writing here a relationship for refractive index of violet upon refractive index of red, this will be written as refractive index of violet with respect to the red will be equal to velocity in a red divided by velocity in a violet. So refractive index of violet being greater than that of red, this value will be greater than 1. So velocity in red color will be greater than velocity in violet color. So can you arrange here the velocity wise how the colors will be reacting to? Can you arrange the colors in terms of velocity? Velocity of red will be maximum, so it will have the similar approach that of the wavelength. Right? So I can also remember this, that velocity for the violet color is less than velocity for the indigo, less than velocity for the blue, less than velocity for the green, less than velocity for the yellow, less than velocity for the orange, less than velocity for the red. Red will have maximum velocity. Have you seen a spectrum from a prism? So which is the light at the top and which is the light at the bottom? Red is at the top and red is at the top, violet is at the bottom. So why it is red dispersing less? Answer is on the board. That is another reason, or we can put it that the velocity of red being maximum, it suffers minimum deviation. Whereas the velocity of violet is minimum, it suffers more deviation. So that is the logic that we are able to put it down. जो प्रिज्म में पढ़ने वाले हैं ना, वो यहीं पर हमने देख लिया है कि वैसे क्यों होता है. Normally we say that refractive index is inversely proportional to wavelength. But when you go for a higher level optics, it is inversely proportional to the square of the wavelength. So this fact is many times used as an objective. But if this is a challenging part, but you should always mark refractive index inversely proportional to lambda only. But if some options are there, 1 by lambda square, then that is also true. So you should be aware. It is known as Cauchy's relation. C-A-U-C-H-Y, Cauchy's relation, where you are able to have refractive index inversely proportional to the wavelength square. Formula list कहाँ तक पहुँची है? 73. Okay. So now we are looking at Snell's law. The problem with the Snell's law that you have quoted do not give you the clear picture that sin I upon sin R is equal to refractive index. We never quote the Snell's law in this manner, even though books are quoting about it, because that do not make us use the formula effectively. So what we quote here, a Snell's law, is simple mathematical relation, that is mu multiplied by sin of theta is equal to constant. This is representing the Snell's law, where you are able to see that mu is the refractive index of medium and theta is the angle in a medium. This is representing to you the Snell's law. Now, how to use it is extremely important. For example, let us consider here that we are having a boundary separating the two medium This is medium 1, medium 2. Or I can put it down here, this as medium 1. This is representing to you medium 2. Okay? And the light is incident from a medium 1. So we will be showing here the light incident from a medium 1. Then at the point of incidence, you will be calling this as angle of incidence I. As it is traveling from, suppose I am having refractive index of 1 here, refractive index of 2 here, refractive index of 1 is less than refractive index of 2, then in that case, the ray, instead of traveling along a straight line, it will bend towards the normal. It is bending towards the normal. This angle, you are calling it as angle of refraction. Am I right? Can I call this angle as delta? Can I say that this is the angle delta? Because it is representing angle of deviation. So in this case, I will be able to write down angle of deviation is equal to I minus of R. Number kahan tak hua tha? This will be? Able to get this? Now see how the Snell's law we arrive at. We say that refractive index of the first medium multiplied by sine of angle of incidence is equal to refractive index of second medium multiplied by sine of angle in a second medium. So if you rewrite this relation, you will be having mu1 upon mu2 is equal to sine of R upon sine of I. Am I right or not? Or I can rewrite here sin I upon sin R अगर लिखना है मुझे, तो you will be having mu2 upon mu1 is equal to sin of I upon sin of R. Am I right or wrong? So by definition, can I write down refractive index of second medium with respect to first is defined as sin of I upon sin of R. This is my 23rd relation today. Getting it clearly? All of you are getting these relations? Now in this case, I am aware of the fact that mu1 is less than mu2. So you will be able to write down mu2 upon mu1 is greater than 1 since I have used the condition mu1 is less than mu2. Am I right or wrong? So if this is true, I will be able to write down here sin I upon sin of R is greater than 1. So you will be having here sin of I greater than sin of R. So you will be having here I greater than R. You can check with the picture. You will be able to see that you are having angle of incidence greater than angle of refraction. Consider the same situation. Again, I am showing you the boundary between the two media. You are having here medium 1. This is representing medium 1. This is representing medium 2. Refractive index is mu2. Refractive index is mu1. You are again having the same situation here that the value of mu1 is less than mu2. So can you tell me which one is the rarer medium, which one is the denser medium? mu1 is rarer, so this is representing to you the rarer medium. And this is representing to you the denser medium. Right? Now the light is present in a denser medium. So this is now representing the source that is represented in a denser medium. It is having the ray of light incident along this direction, At this point, you will be able to draw this as the angle of incidence. The ray is expected to travel in a straight line here. Now ray will be bending away from the normal in this direction. This is representing angle of refraction here. Am I right? And I can say here that it has the ray that has bent away from the normal. So this will be giving me the angle of deviation now. Am I right or not? Got it clearly? Now, when I'm using the Snell's law, I will be writing here mu2 into sine of I is equal to mu1 into sine of R. So if I rearrange this term, sine of I upon sine of R will be equal to mu1 upon mu2. Am I right or wrong? So from this part, mu1 is less than mu2, so this will be less than 1. So in this case, sine of I will be less than sine of R. So you will be having angle I less than angle R. You can check the picture. You will be able to see that angle of incidence is less than angle of refraction. Now relation changes here. We are clear in this definition that what relation we are using. I can rewrite this relation here in this manner. I can write down sine of I upon sine of R. This will be equal to refractive index of 1 with respect to 2. And here I have written refractive index of 2 with respect to refractive index of 1. So actually the relations have changed. Have you noticed that the relations have changed? And that is why you should always remember the Snell's law as mu multiplied by sine of angle of incidence or refraction in that medium. You should not memorize it simply mu is equal to sine I upon sine R, because that will not give you the complete picture. Every time you have to check it in this manner. Then only your answers will come correct. Otherwise, it will have some errors in it. Ho gaya? Finished? This will also prove that why the light is bending towards the normal or light is bending away from the normal. Check it out, you will be able to see that. Like in the first case, you can see here that angle of incidence is coming out to be less than angle of refraction. Sorry, angle of refraction is less than the angle of incidence. Now, if you want the angle of refraction to be less than angle of incidence, then the ray should bend towards the normal. Am I right or wrong? Similarly, in the second case, you can see that the angle of refraction is greater than angle of incidence. If you want the angle of refraction to be greater, the ray has to bend away from the normal, then only angle of refraction will be greater than angle of incidence. Got me clearly? So this relation mu into sine of angle theta is constant, is the Snell's law in a real sense. This will never give you the answers wrong. Ho gaya? Write down there. If an object is placed, in a medium of refractive index mu1 at an actual distance d suffix AC, at an actual distance d suffix AC from the plane boundary, and when seen from a refractive index, when seen from a medium of refractive index mu2, when seen from a medium of refractive index mu2, it appears to be at a distance small d suffix ap. Now, are you aware of this situation, what you have written? There is a small game that you can play. Fill a bucket with the water and place a coin inside it. And see that you are giving him certain horizontal distance. I mean to say that if this is a table from here to here, you are keeping the bucket at the center of the table, the bucket is full of water and there is a coin placed in it, the person will be standing like this, away from the bucket. And ask him with the help of a stick to touch the coin. You will find that he will be unable to touch the coin because of difference in the appearance. What exactly happens here is you are having, suppose a medium, we are calling this as a medium whose refractive index is mu1, and there is medium whose refractive index is mu2. You are looking from above, so your position of eye is here. So from this boundary, this is the D actual, the object is placed here. This is representing D actual. But due to the vertical vision from here, the object would appear to you somewhat here. So this is called D apparent. This is representing a denser medium. This is representing the rarer medium. Are you getting the situation? If you are placing a coin, the coin will appear to you elevated, as if when you are putting the specs, the floor was appearing to you elevated the same way. And that is the reason nobody will be able to touch the coin. Okay? But you can touch it very easily if you are making angle of incidence 0. Because when angle of incidence becomes 0, angle of refraction will be. So no refraction will be taking place, then D apparent and D actual will appear to you exactly the same. So there is a condition for no refraction to take place that will be just coming after this point, and then I'll explain you the part. So this is the situation that you have written in this format. So write down there, refractive index of first medium with respect to second medium. Refractive index of the first medium with respect to the second medium will be equal to refractive index of the first medium with respect to second medium will be equal to D actual upon D apparent. This will be adding to your list. Which one is denser, which one is rarer, that you can look at it. We'll have some more about this also. But I have one more thing for you to tell, that is a condition for no refraction. So can you write down there, condition for no refraction? The one condition which we have already discussed. So write down there, if angle of incidence is 0, angle of incidence is 0, angle of refraction will be 0, and there will be no refraction. Is it possible at any moment of time that angle of incidence and angle of refraction are equal? Is it possible at any moment or any situation where angle of incidence and angle of refraction will be equal? I am talking of incidence and refraction. Where? There is no principal axis here. Principal axis will be related only to the concave convex mirror or the lenses. In this case, is it possible that angle of incidence and angle of refraction may be equal? Is it possible, yes or no? Is? I'm asking you equal. Then it will be angle of reflection only. It will not be angle of refraction. It is called total internal reflection. I am not talking about total internal reflection. So this is the second case for no refraction. If you are able to see that angle of incidence and angle of refraction both are equal, then there is no refraction. Is it possible? Yes, it is possible. How and where it is possible, you can check it on the board. Suppose you are having here two media. This is having the refractive index mu, this is having the refractive index mu. The ray of light is coming from this first medium along this direction, will be incident here, then without deviation, it will be moving straight here. In that case, angle of incidence and angle of refraction will be equal. Because refractive index is not changing, so refractive index is same, so medium is same. If medium is same, refractive index is not changing, then angle of incidence will be equal to angle of refraction. There will be no bending at all, so there is no refraction. Getting it? दो conditions कौन से बताए मैंने? If you are having the normal vision, that is angle of incidence, you are making it equal to 0, then there is no refraction. Or if you are having the same medium there, two mediums of same refractive index are taken into account, then you will find that there is no refraction. Okay? Getting it? Now, why you are finding the floor to be elevated when you are putting the specs for the first time? Change in medium is not taking place. Loudly, please. Today also you are putting the glass, but you don't feel the elevation in the floor. Today you don't find the elevation. Can you find the elevation today also? Now, what is happening is very important. First, at a very young age, you have got the specs. So probably your father, mother have scolded you for not taking care of yourself, not eating what they call it as carrots and what else to improve the vision, right? Then they took you to the ophthalmologist. They have checked, they have given you the number, your headache is gone. And then they take you to the optician, he makes the glasses for you, specs for you, and then your father, mother tells you that handle it carefully, otherwise it will break and again you will have a problem. So what do? You put down the specs, but to handle it correctly, you look like this. The neck is moved up. So what you are doing? You are increasing the angle of incidence. And when you are increasing the angle of incidence, angle of refraction will be also increasing. That is the reason why it appears to you as elevated or bended there. Now today you have realized that even if you are looking down, the specs is not going to come away. It's going to stay here. So what you are doing? You are making the angle of incidence 0. When you are making the angle of incidence 0, you are able to see that there is no refraction. That is why the floor today is not appearing to you to be elevated. Now you have adjusted with that. Eyes are not getting adjusted. You have adjusted your vision to such an extent that always the rays will be coming with an angle of incidence equal to 0. You can do like this and check it out whether the floor is moving, yes or no. If you move the specs up and down, you are able to see the floor moving up and down. Is it appearing to you? Yes or no? So this is because today we are accustomed to use this particular specs. Even if we are looking down, we are making the angle of incidence 0, so there is no refraction. And that is why our eyes have not got adjusted. We have adjusted our vision so that angle of incidence is becoming always 0. Right? Similar question was asked to you that in this classroom, do I have 2 positions? For those who are not wearing the specs and for those who are wearing the specs. Have I raised or not? So those who are wearing the specs, they should look into that corner and then try to look at me. You will find that my position is changing. Your orientation should be in a corner and your eyeball movement should be onto the left. Then you will find that the position appears to be slightly different. Now what you are doing, you are making the use of neck. Whenever you are looking at me, you are adjusting the neck in such a manner so that light coming from me is having the angle of incidence on the spec surface to be equal to 0. So when angle of incidence is becoming 0, angle of refraction will be also 0. Yes, that way I am expecting. To actually look onto this side, my orientation of neck is like this, but I am looking at you like this. Then you will be able to see the difference. You can check it out because in that case, the angle I am increasing the angle of incidence. So refraction is bound to happen. If I am taking here the angle of incidence to be 0, what you are doing, like you are sitting in front, you are looking at this angle to me. Your neck is orientation in this manner. When I am looking at him, he is looking straight. So everyone who is having the spec, they try to align their neck in such a manner so that angle of incidence is always 0. So there is no refraction here. Are you getting the answer for that? Why there is no refraction? So you have to understand how these things are all working here. If you create a refraction, then there will be a shift in position. If you don't create the refraction, then there will be no change in the position. That is why all the students, whether wearing specs or not wearing the specs, are looking at the same position, not at the different position, because they have the neck to move around and align that neck in such a manner that angle of incidence is always equal to 0. We have to discuss that. It's a big story that we'll be covering in the next part of it. But these are the 2 questions that I have explained to you. Sairam.